Tell me what this graph is going to look like after this intervention.
So
Loud.
X1 is going to look exactly the same.
Okay.
Sorry, mate, there'll be an I going into it, right?
An I going into X1, yes?
X4 isn't going to have any arrows going into it anymore except for a new I going into it.
X4's arrows from X2 and X3 are going to vanish.
And then there's going to be an S going into X3. Oh, is that a different example or is it all the same?
No, you got it right.
Okay.
So that's it. That's the actual post-intervention graph.
Why can't the direct graph between X1 and X3 be broken?
Well, what I've said in the assumption is that the intervention is hard on X1, and that leaves the downstream effects intact. And the intervention is soft on X3, right, which also leaves the arrow in place, even though it changes it quantitatively. And that's the difference between a hard and a soft intervention. So that's the actual post-intervention graph. So if I was to do that intervention, right, the system I'd be getting data from post-intervention is represented here. If I didn't do the intervention and I actually looked at it with just passively collecting data, the system I'd be looking at is on the top. So the moral of the story is that the system you collect data from, right, if you do an intervention, can be different than the system you collect data on if you don't do an intervention. Right? Yeah?
Why is there not an X between X1 and X3? Like, aren't we breaking the connection?
Well, because first, a hard intervention doesn't actually change arrows downstream from the target.
I'm so sorry.
That's all right. And the soft intervention doesn't change arrows anywhere.
I just need to hear it again. Sorry.
Sure. Yeah.
After the intervention, it's not one, it's like two graphs now.
Sorry?
That's two graphs now of future. X4 and X6 is
It's disconnected.
disconnected. So they're two now. It's not one.
So it's essentially
That's still one graph, but the graph has, you know, some chunks of it that are disconnected. So yes, that's true. It's still one graph, though. I mean, a graph is just any set of variables and set of edges, right? So if there's no edges, that's still a graph. Right, but that's the way the graph looks after it. And so you can say that's sort of like two graphs. Right. Okay, so that's the system you're collecting data from. Okay, so now if I do the same thing, right, and I say, okay, what's the pre-intervention graph going to look like if I do a hard intervention on X3 and a soft intervention on X6 and X4? What's the post-intervention graph? It'll look something like that. So none of the arrows change from the soft interventions, but I add a little variable to make that clear. And what does change is the arrows that go into X3 because I've targeted that with a hard intervention. Okay, everybody clear on this? It's a reasonably straightforward mathematical operation. Okay. That's the whole theory of qualitative causal graphical models that I'm going to give you, right? It's that simple. It's just graphs and what happens to graphs in the response to interventions that I can actually model. So far, no numbers. That's the qualitative picture. But it's still actually quite a powerful one when we introduce the connection between qualitative graphs and qualitative statistical relationships. Yeah, somebody had a question? No. Okay. So now I'm going to segue into where we actually add parameters, probabilities, quantitative relationships on top of these qualitative relationships. And what we do is we say we're going to interpret these graphs first as parametric models. We're going to give them a parametric family, interpret it, and then once we've done that, we're going to actually assign particular values for the parameters in the models, and once we've done so, we will have an instantiated model, and then from an instantiated model, right, we have a full specification of a probability distribution from which we can sample to get data. So our next steps are, what are the parametric families that are simple and we can actually do with the program easily, right? Put in actual numbers, get instantiated models, simulate generated pseudo-random data. Okay, that's what we're heading. So here's a picture of the program in which I've taken a graph and I've, right, interpreted it in two different ways. One, right, as a Bayes parametric model, which I'll get into, and the Bayes parametric model involves discrete valued variables, right, like gender, right, or something of whether or not you are considered low or high on some property, or whatever variable you want, it's only discrete values for this parameterization. We'll talk later in the week about mixed models in which some of the variables are discrete and some of the variables are continuous. But the other really simple parameterization is called structural equation model, or SEM, and that involves all continuous variables and linear relations between them. And there's lots of stuff in between, but we're not going to get to it right away. Okay. When I go to the next level, what I do with a parametric family or a parametric model to instantiate it is I have to put numbers in for the parameters. So if I've had, right, a simple model and one of the variables was, right, smokes, right, and I said it's a discrete variable with yes or no only as its values, I've got to put in the probability for smoking and the probability for not smoking to make it an instantiated model. Okay, so the first class of models are called Causal Bayes networks, right, and they're as old as the field, and the idea is to take a graph like this one, and in this case I've just made all the variables 0, 1 binary discrete variables, and I'm going to build the joint distribution over those three variables, which is notated as the probability of smoking, yellowed fingers, and lung cancer, right, by multiplying three factors, right, one for each variable in the graph, conditional upon what the graph says is the direct cause of that variable, right? So in this case, smoking has no direct causes, and so I don't put it conditional on anything, I just give its marginal distribution. Yellowed fingers is caused by smoking only, so I condition on its one cause smoking, and lung cancer is also caused by smoking, so I condition it on smoking. So this joint distribution factors, according to the causal graph, right, this is the probability of the variables or the product, right, of each variable conditional on its direct causes. And that's what it ends up looking like, right, in the actual equation. Okay. So, I mean, one of the advantages of doing it this way is, right, I'm now parameterizing the distribution, right, as a function, theta, that's the parameterization, right, where if the variables are all binary, I can do this graph with 5 parameters, right, because that's the entire joint distribution factorized. So for the probability of smoking, I have to give a parameter, let's call it theta 1, for the probability that smoking equals 0. And then the probability that smoking equals 1 is just 1 minus theta 1 because they have to add up to 1. Right? So there's only one parameter necessary to give the marginal distribution for smoking. And here, right, for yellowed fingers, right, given smoking equals 0, there's one parameter, but then I also have to give yellowed fingers when smoking equals 1 because theta 2 and theta 3 might be different. So this distribution in this graph can be given in 5 parameters. Now, right, let's suppose, right, that it was a different graph in which now I had yellowed fingers causing lung cancer, and so all the variables were connected by at least one edge. Well, then the same idea, right, now has to add yellowed fingers into the distribution that lung cancer has conditional, and that would add another term, so now I'm going to have to use 7 parameters for this distribution instead of 5. So by taking out that edge from yellowed fingers to lung cancer, I reduce the number of parameters by 2, and in general, right, every time I take out an edge in a graph, I reduce the number of parameters I need to write down the joint distribution when I can factorize it in this way. And just, excuse me, just backing up historically for a second, it's interesting to note that when robotics was sort of going this direction of trying to actually get robots to represent the world with probabilities as opposed to logical rules or rules, right? It was very quickly realized that there was a lot of information that you're going to have to get the robot to store, right? And any way we could reduce that information was going to be very helpful in getting robots to actually function reasonably, not only in what we could do to initially program them, but also how they would actually learn information about the world and update the information they would have to carry around. So if you if these graphs are sparse and they have fewer edges, then the number of parameters that the robot has to actually have goes way down, and then the number of things the robot has to do when new information comes in gets reduced a lot. And so a lot of the early work in this field of graphical models was in service of making robots efficient enough to function. Causation came a little bit later. Okay, so here's a case where I put in actual numbers. Right? So now this is not just a parametric model like this is an instantiated model. Numbers are actually in there. Okay? So if I asked what's the probability jointly that smoking is 1, yellowed fingers is 1, and lung cancer is 1, right? That's computable by going through and factorizing this distribution in the same way that I said before. I need to know the probability that smoking equals 1, the probability of yellowed fingers equals 1 given smoking equals 1, and the probability of lung cancer equals 1 given smoking equals 1. So if I just look up in the table, the probability of smoking equals 1 is 0.3. Yellowed fingers equals 1 given smoking equals 1 is 0.8 right there. And the last one is 0.2 right there. I multiply that out. That gives me the joint probability of those three things happening at the same time using this table. Easy? Clear? Okay, so now you could all do that if I asked you to. Now, let's see how this translates into what happens when I make a hard intervention on the graph and how that translates into different calculations about the probability, right, of things happening that that graph describes. Okay, so let's imagine now that I do an intervention on yellowed fingers, right, and right, I have this distribution up there that expresses the joint before I do any intervention. So without looking at the slides, like Lizzie says, what do you think I'm going to do to the joint distribution to represent what happens here? Any ideas? Yeah. Remove what? Right here. That's correct. And what do I replace it with? Well, I can't replace it with nothing. So I got to replace it with that. With yellowed finger given my intervention. My intervention actually is now setting the distribution for yellowed fingers, whereas prior it was set by smoking. So that's exactly the right answer. And then the other thing to notice is the other terms get carried down unchanged. So that's it, right? And what we say is this is the manipulated distribution. So the difference is very localizable into exactly the term in that factorized joint that I've intervened upon, or the terms. Yeah? So suppose I said, I'm going to actually take everybody and flip a coin. If it comes up heads, right, you wash your hands with tar stains, tar solvent soap. And if it comes up tails, I paint your fingers with tar. It erases the information about whether smoking makes your finger stain. Or I might do it instead of 50-50, right? I might say, I'm going to flip a loaded coin, or let's say a set of dice, and if it comes up, right, as a 12, right, you get tar stains. Anything else, you get clean fingers. So that distribution is my choice to set. But the default is always 50-50. And of course, we know that the distribution of tar stains on people's fingers now is not 50-50. Most people, right, don't smoke, and those who do smoke, right, if they actually smoke filtered or something else, they don't really have big tar stains. But back when all these examples were put together, some people were rolling their own cigarettes, right? And when you're rolling your own cigarettes, you get stains on your fingers quite vividly. So there was a time where looking at people's fingers could tell you a lot about how much they smoked. Yeah?
Is the number of parameters equal to the number of variables, not the number of agents?
It's a function of those, but it's not equal to it, right? So if I have, it is a function of three things. The number of variables, how many values each variable has. So if there's 3 values as opposed to 2, I need more parameters. And it's a function of the number of edges, right? Well, if it was, for example, if all the variables are binary, right, then the number of parameters is 2 to the number of variables minus 1. But if it's a sparse graph, it reduces it. I mean, it can be linear.
And if it's cyclic, it's minus 2?
Well, I've not talked about cyclic graphs.
It depends on the arrangement of the edges too, right? Like
Yes.
with binary variables and about that.
I mean, yeah, and it's a reasonably complicated formula, so it's not simple. But the maximum number of parameters you're going to need, right, is essentially the number of values, right, to the power of the number of variables, right, minus, right, whatever it takes to get to sum to 1. But this is the key fact, and you got it exactly right up there, that you're going to replace exactly the term of the variable you've intervened upon by changing what's conditioning, right? Prior it was the variable in the graph that you were, right, assuming influenced that guy, and now it's your intervention, right? So to be concrete, right, we had this originally, and now if we took the same graph but intervened on yellowed fingers, where we set the distribution of yellowed fingers equals 1 to 0.5, right, which we don't have to do, and we did the same calculation, right, we now multiply 0.3 times 0.5 instead of 0.8. 0.2 is the same, and so now we change from 0.048 to 0.03. Okay, so that's the difference there. So that will give you a very general method for computing the regular probability of any particular array of events, right, before an intervention, and the same array of events after an intervention. Right? And in some sense, this is the key thing you want, because obviously if we want to know what's going to happen if we do something, we need the bottom, not the top. Right? Now, it's a subtlety that we're not going to get a lot into, but you can see that what I've done here is give you a method for computing the manipulated probability, right? If what? If I know the causal graph. So this all assumes that I know the causal graph. If I don't know the causal graph, but I know something about the causal graph, you can still do a lot in certain circumstances, but it's much more complicated, right? So there's a really cool state of the art, which is how do I actually compute manipulated probabilities? When can I compute them, right? If I don't know the whole truth about the graph, but I know something about the graph. Okay, and calculating the effect of a soft intervention, right, is similar. Now let's see if you can predict what I'm going to do there, right? So suppose now I just do a soft intervention on yellowed fingers, not a hard one. Same question. What do I do? What does the new distribution look like? Sorry? Yeah.
Your rule doesn't change the distribution.
My rule, so it's the same distribution as was on top. How many agree? How many disagree? Oh, looks like you're not going to do well on this one. Okay, somebody who disagreed, give me another. Huh? No, the variables are the same. So the only thing that's going to change, right, might be, like in the previous thing, what changed is probability of S stays the same. The probability of YF given S changes to YF given I. Probability of L given S stays the same. So I've modularized which part of the distribution I've changed. Now, same thing for the soft intervention. Yeah?
You have the same thing, but you have another probability term. Probability of those things given the soft intervention.
Okay, so you say the only change is it's yellowed fingers given S. So be precise. It's yellow finger's given exactly what? I? No, there's no I because it's soft. Okay, so it's yellow fingers. Oh, bad choice of symbols, right, sorry. Red S. So you say it's yellow fingers given red S. Anybody else? And the green S. That's the answer. Right? So I'm replacing it because I'm not replacing the influence of S, I'm changing the influence of S. So that's the distribution that I'm going to get to. Right? So this term right here says I still have to include the influence of, oh, this is a terrible choice of colors and symbols. I apologize profusely. But you can see what the idea is here, right? So I've now replaced this yellow fingers given smoking with yellow fingers given smoking and what the soft intervention was. Right, and that's the manipulated distribution there. Okay. Everybody good? Okay. Yeah.
Soft intervention in this case would be still we have a soap, but it's easy to wipe out for the smoking guys, or how
The soft intervention in this case might be something like, you know, I spray a little bit on your finger, so if it had stuff before, right, it's now even darker. And if you had nothing, it's a little bit, but I don't change or erase what was on your finger before. Yeah.
The left side a button joint distribution and also add as a prior yourself to the right side?
I certainly could do it that way, right? So usually I don't put the joint distribution, right, that includes the intervention term, right, but I could. And then it would be just a completely separate term saying what's the probability of that intervention. So that's a really good point. I didn't put that in there, but I could put, right now, the manipulated distribution moves from the probability over YFS and L to the probability manipulated over YFSL, comma, and soft. It's a joint among four things. But to make things at least as comparable as possible, right, we're just going to look at the distribution over the same variables that I started with. Yeah.
On the left side, that's where I'm saying that
Assuming that the probability of soft is 1, and therefore the term is 1, and therefore the right doesn't change.
That's the way we look at it. Yeah. But you're right. That's a good technical point. And to be fully precise about it, I should include it as well.
The probability of the soft is equal, so it means that it doesn't change the whole model.
He's definitely going to do a soft intervention. That's probability 1.
Okay, so it means that my answer was correct because the probability of soft was it.
No. Your answer was not correct because I didn't replace YF with just soft. I also had to add in S.
What is the probability of the soft?
The probability of the soft, right, is going to be depending on what you choose. So if it's, right, 50-50, the probability of soft equals whatever it is to equal 50, but the probability of summing over all the values of soft is going to be 1.
Probability of the intervention versus the additional probability of the variable that's induced by the intervention. So the reason that we're excluding the probability of the intervention itself is because the intervention occurs with probability. However, given that there's an intervention, the probability of the yellow fingers, that's something which could be any distribution.
Let's come back to this. I don't want to spend, but I think the idea, right, should be, because I'm not going to pursue this right in detail, but the idea should be clear in the sense that where you're changing the distribution from the pre to the post manipulation is localized in the target of what you're doing, and if you do a hard intervention, you're going to eliminate the previous thing, and if you're doing a soft, you're just going to add the soft to it. Okay, that's the basic idea. Okay. Let me go back now, and now I'm going to show you, right, how in the program to actually go from qualitative graphs to I'm going to build a parametric model, right? So I'm going to do the first thing for smoking. Okay, so in the program now, I have my graph, right, which is smoking causes yellowed fingers and lung cancer. And I go to the left hand and I click on parametric model. I put that into the workbench. It's not inhabited or populated yet. So I go and I connect it to the thing above it in the same way I built the causal graph. And what that tells the program is that the parametric model I build here must interpret this graph and not some other graph. So the graph matters to the parametric model. And let's see how. So when I open that up, I have a choice. I could do a SEM parametric model. I could do a Bayes parametric model. I could do a generalized SEM, which I'll get to either later today or tomorrow. But for now, let's do a Bayes parametric model, because that's one thing that I've just described. So I make that appear in the highlighted field, and I say OK. And then again, I get this set up manually or do it automatically. Do it all manually at first. Click OK. And then I get into the spot where I've got to actually do the work for each of the variables. So what's involved at this point parametrically is just how many values each variable has and what are the values. That's all you have to do to parameterize, right, to set up a parametric model for the Bayes case. So the variable highlighted is LC. That's lung cancer. And on the right, it says category names, and each of the categories, right, has so this is 0 or 1. If I wanted to switch that to something else like, no and yes, I could do it that way. And then if I click on a different variable like this, I can go to the presets, which have conveniently given me the kind of options that occur often in discrete variables. So I could do low, high, right? Low, medium, high, on, off, yes, and no. For us, if I do low, high, right, I would get that. And if I do yes, no, I get that. And yellowed fingers, I could do the same thing, but do low, high. Okay? So smoking is yes, no. Lung cancer is no, yes. And yellowed fingers is low, high. And if I wanted to do lung cancer as 3 values, I could click on the number of categories, go up 1, and it adds, right? And then I could do no, yes, right, intensely yes, or something, right? And that's all. I've now built a parametric model, okay? So you guys go ahead and do the first thing in a minute. Let me show you the next set of steps, right, that allow you to go ahead and put in the actual numbers. Okay, so I go to the left here and I go to instantiated model, and I click on that, and then I pull an arrow from the Bayes PM, which is now labeled here, and to the IM. I double click on that, and the pull down should give me, right, a few choices here, but only choose the Bayes instantiated model for now. Click OK. Again, you have a choice to do it manually or randomly. Choose manually. And now you have to actually put in the numbers. So let's start out with smokes. I now have 2 fields to fill in. The blue that says smokes equals yes, and the white that says smokes equals no. And now I have to put in probabilities. So what probability would we like to use for smoking equal yes to accurately represent the population that we live in right about now? Anybody know what proportion of people actually smoke in the US? 8%? It's higher.
In the adult US population, based on the race, it differs, but it is almost 20%. So it differs 18 to 25%, almost 20%.
Let's type in 0.2. So 0.2 is my, right, and I get to decide the truth here. This is not like correct or incorrect with the world. I am playing God and defining the truth that's going to generate the data. Now, instead of going and typing 0.8 for smoking equals no, the program allows you, if you hit the tab button, right, it'll automatically fill in whatever the rest of the values in that row have to be in order to add up to 1. Okay? So now I've described, right, the probability marginally of smoking. Now let's go to yellowed fingers. Now I have 2 rows. The first row tells me what are the probabilities that we'll have someone with low levels of yellowed fingers, right, if they smoke. So that's pretty low. So let's make that, let's say 0.2, and then 0.8 for high. And what if they don't smoke? So now I'm making this very different. So if you can read that from the back, right, the probability of yellowed fingers equals low, given that you don't smoke, is 99%, 0.99. And the probability of having high yellowed fingers, given you don't smoke, is 0.01. What kind of cases might that represent? Well, suppose you don't smoke, but you like rolling cigarettes for your friend who does, right? So that's still possible. Yeah?
If you have a structural 0, clearly the probability of the yellow finger given no smoking is 0.
Yeah, you can just put it, you can put a 0 in. And that shouldn't present many problems except in a couple different places. So if I wanted to say 1 here, right, I can do that too. But that's not very interesting for the numbers, so let's do this. And then if I do lung cancer, right, I have to now do 3 values for each one. This is the probability of lung cancer equals no, 0.5, let's say, right, 0.3, and intensely 0.2. I mean, that's not accurate, but this is something you might put in. And then what's the probability of lung cancer equals no, given you don't smoke, right? Well, presumably that's a lot higher. So when you look at what the causal influence is that you've put into this model parametrically, it's the difference between the rows. Not the row, it's the difference between the row. So what influence does smoking have on lung cancer? Well, you might say it's the change in probability from 0.2 to 0.3 and from 0.1 to 0.2, right, of getting cancer or getting intensely a lot of cancer. Okay? So that's where we put in to these models, right, the level of the causal influence. Why is my battery running low? Okay, so now I want all of you guys to go back and go into your program and do what I just did for the yellowed fingers, smoking, and lung cancer example. Put in a parametric model, put in an instantiated model, put in numbers that you think make sense or are interesting, and then do the same thing for your 4-variable model that you did all by yourself with different variables, and we'll walk around and help you. And so when you finish doing that, you will have fully specified a causal statistical model, right? And then from that, you can generate data, which we'll get to in a little bit of time after that. Okay? So let's take 10 or 15 minutes now. We'll walk around and help you, but go ahead and build parametric model and instantiated model as I've showed here in the program.